So we are users of data, and we use XBRL data as well as AI or machine learning, as I prefer to call it usually. And I would like to address some claims that I've heard from many people who are charged with making XBRL reports recently, saying that they didn't need to pay so much attention to it because AI was going to actually do the work of analyzing reports for them. And in my opinion, as someone who uses inline XBRL for machine learning, that's of course an absurd claim. But I don't want you to just take my word for it. I would like you to be convinced of it. And I'm going to introduce you to actually what machine learning is and what we need to perform it to actually prove to you that we cannot do it if we don't have structured data to learn from. So first, that's going to be by introducing the terms, what is really AI or machine learning. So when we do machine learning, we are trying to make a task that takes some kind of input and tries to get some output, right? So for instance, we are trying to make translation of Italian into English, or we are trying to get a feed of the front of a camera and deciding how we need to steer the wheel, that kind of issues. And they are issues that we cannot describe easily. If we want to solve them, it's very hard to give some precise rules of what we want to do. So instead of trying to figure out what are the rules of making this task, we instead have the idea of saying we will give examples of inputs, right? Many examples, and we will take our imperfect process, see what it produces on these inputs, right? So for instance, we have an imperfect translator, give it a lot of Italian sentences, it will make a lot of English sentences, and then we will try to see how we need to improve that. So that's learning, right? Just like the human brain does. In order to do that, we actually need to define what is an improvement, right? How do we actually define that the translation is better than another one? So that's what we need to do, and there are different ways to do that. Now, generally speaking, with machine learning, we have defined efficient ways to do that so that when we decide that something is better than something else, we know exactly how to modify our algorithm to produce that result, right? Even so, just knowing how to improve the algorithm is not an end in itself, and you can know ways to improve your algorithm an infinite number of times without ever getting a good result, right? So just because we know how to infinitely improve the result doesn't mean we actually get a good result in itself. But coming back to our issues of defining how you tell that your algorithm performs better than it was previously performing, there are different ways to do that. The first and the most simple is to be able to give a number to your algorithm to say how well it does, right? To have a score for your algorithm. For instance, if you're trying to identify images, saying which image contains dogs, then you would be able to have training sets that sometimes have dogs, sometimes doesn't, and you can compute the percentage of times your algorithm gave the right prediction, right? So if you make a new version of your algorithm and it predicts things correctly, you can say it improved. That's not always possible. So for instance, let's say you are trying to make chatbot and you want it to be able to answer any prompt. And for instance, you're going to test your task with a prompt like, write me a horror story. So you're going to test two different programs, and they're going to give you two different horror stories. It's very hard to come up with a score for that, right? If you were able to evaluate which one is the better horror story, you wouldn't have this problem in the first place. So the only way to do that is to actually ask a human, which of the two stories do you think is the best one? So just think about that. That's quite inefficient, right? When you have a score like computing the accuracy of a prediction, you can compute 1 million of examples in a few seconds. If you take a human and you ask him to judge what the better horror story is, in a few seconds, he's maybe going to have one execution of that. So would you trust a company that uses the latter thing, right? If a company tells you, I'm going to train my machine learning algorithm by having humans look at answers, and then for each answer, they're going to give me the answer of, is it better? Would you invest in that company, for instance? What would be your intuition? Well, There's one company that does that. It's called OpenAI, and there's a program called ChatGPT that was trained like that. So don't always trust your intuition on that, right? Now I'm going to introduce what we call supervised learning, and we have spoken about SCORE. So usually you want to train your algorithm, like I said, by comparing, by improving on the outputs. There are some times where you can only use the inputs and the output to compute your score. So for instance, let's say your task is only to make copies of the inputs. So let's say you have images and you want to make compressed images that look like the inputs, right? Just by looking at the compressed image and the input image, you can count the number of pixels that are close to one another, right? So you can just compute a score from that. But so if you want to train that kind of algorithm, you could just pull 1 billion images from the internet and then train your algorithm directly with that. Now imagine your task is telling if an image includes a dog. You can pull 1 billion images from the internet. You can use 2 versions of your algorithm to predict whether the image contains a dog. And then you have one version that tells you that the 5th image has dog, and the other version tells you that it doesn't have dog. And then how do you know which one is the best one? You don't have an algorithm that tells you which one is true, right? By definition. So you have to have a human go and look at the 5th image and tell you whether it has a dog or not. So if you have to do that on 1 billion image, that's going to be troublesome, right? At any rate, if you want to tell which program is best, you have to actually have some more information, which we call a label for that information, right? So besides the input of the image, you also need to have a human say, okay, this image has a dog, so I want my program to say that this kind of image has a dog, and on other ones that it doesn't have. So you need the input and some extra information about what you would expect the program to give you as an output if it performs correctly. Now let's look at what it looks like when you are dealing with text, for instance. So let's say our task is to tell which 3 words in a text are the most important. So your input will be text the sort of text you would like to make a prediction on, and your label will be, for instance, the 3 most important words you have in the text. Now, having the input and the label separated is not always convenient. For instance, there could be several versions of the same words in your text. So usually if you want to have some precise things, you also want to get the position. And one efficient way to combine the information about the position of what you want to predict text is to mix them. Right? So for instance, you could directly have the information of which words are important and in which order they are most important directly in the text. So if any of you have ever opened technically an inline XBRL file, that should be obvious to you. This is very close to what we do when we do inline XBRL. Right? So inline XBRL very naturally will act as a training set for supervised learning. And the most obvious task you would have for that is you would want to learn to identify an XBRL attribute in plain text, right? So for instance, you would like to identify the name, right? So which concepts a number relates to, or what is the scale, that kind of information, right? So that is most obvious task. So the first application you would have thought would be to, like I said, predict the names. So very simply speaking, for instance, just being able to identify which technical elements or can be correspond to which disclosures. So what you would expect, of course, is to have a definite prediction. So using some context, right, to see from the whole text what just one part means. For instance, if you have goodwill above intangible assets, you would like the second number to be intangible assets other than goodwill. And of course, you don't want to have to describe rules for every instance of these elements. You have 4,000 elements in a taxonomy, so you would like the algorithm to learn that by itself. Now, in trying to predict things, we can often see that it's not always clear what the element means. And of course, a nice way to see that would be, for instance, if you have only one line intangible assets, usually you're not going to have just one element that could fit there. And the output of your algorithm will be a prediction of how likely it is that something is there. When you see something that looks ambiguous, that can be a sign either that presentation actually is ambiguous or that you're lacking context, right? So Usually the information about whether you actually have goodwill in that will be present in the note. So you could ask me, why don't you just give the whole document from the start? Now, that's where I will talk a little about complexity. Complexity is about how efficiently you can make your prediction. So our machine learning algorithm is trying to get the best result out of all prediction I can. So that's an optimization task. So my algorithm will have, my program will have a lot of different parameters. And I'm trying to find the best parameters to make the best prediction. So usually in standard machine learning algorithms, the more parameters you have, the longer it takes, and it's usually pretty linear. But the number of parameters you have in your program gets much higher the more input nodes you have. So the more words you have in your input text, the more time it takes. And if you multiply the size of your input by 10, the time it takes to compute that will be multiplied by 100, right? Rather than just 10. So we cannot afford to usually just give all the page as context, right? That would be very slow to converge. So just to give you an example, usually if you just give very little context, like just a sentence, we have a program that's going to train very efficiently, but it will actually correctly identify the meaning of the number in quite few cases, usually less than 50%. If you try to give in grade whole document, you would eventually have a good performance, but the time it takes to train your algorithm is way too large, right? So you can always try to parallelize it, right? Having more machines training, but to some extent, there is still a limit because when you add more parameters, you multiply the time it takes to train by a lot. It takes a lot more steps to train, and each step is also much longer. So usually you want to find the right context for it, which is why you start small. Usually you try to predict on a small context. You see whether the result is ambiguous, and if it is, you go and look for more context. You could also ask me, how do you deal with entity-specific disclosures? And the reason why we have to deal with them in a specific way is we are learning from dataset, and entity-specific information is just present in one for one entity. So by definition, we cannot really learn to predict the meaning of entity-specific disclosures. So instead of that, what we try to do is to identify which disclosures are entity-specific. So in that case, we slightly modify our training set. So instead of having labels that are just the name of the elements, we will identify which ones are extensions and try to predict really that they are extensions. So the end result of that is that we are usually able to say in the end result, okay, this looks like something that is entity specific. Usually the accuracy with which we can predict that things are entity specific information is much worse than for standard text, which is yet another argument, I guess, against having too much entity specific information. The meaning of that the training algorithm that has seen all reports existing has a hard time identifying that things are an extension, will tell you that a financial analyst that has a lot of experience and seen many, many reports will also have trouble identifying that something is entity specific, right? This algorithm has seen everything and has learned to make the best prediction it could, seeing all reports, right? So even a financial analyst would have trouble saying sometimes that things are actual extensions. So usually that tells you that the information is not there, neither in the table nor in the actual disclosures. So usually we also have tables where you pretty much only have extensions and entity-specific information. So for instance, information about segments of a company are very entity-specific. In that case, there is little value in trying to make predictions about the table because all of it will be entity-specific. So usually what we try to do is to identify the nature of the table or of the text, and that works pretty well. So we are able to say, okay, this table contains the segment specific, the geographic areas or the segments in which the company operates, and the lines or income statement lines, right? So we get a level higher to have some more information about really what is the meaning inside the table. And then we know that all of it is going to be extensions. So anyway, we can just look at the labels and say, okay, I'm going to create an entity-specific element for the name of the column. Now, there are also other things besides just prediction that you can make with the data you get from training an algorithm. And one of them is really getting feedback on the taxonomy itself and on how it's used. So I will introduce to you one common issue that we may have sometimes when training algorithm, and that's imagine you're trying to create an algorithm that identifies the shape of animals, right? So you ask humans to create your training set, and they will identify which animal is behind the shape. Imagine you have many images of ducks, but you have 20% that have been identified by humans that created labels as goose or geese, I guess. 20% geese, yeah. Right. You could ask yourself, what would be the best kind of algorithm of machine learning end result, right, to make that kind of prediction on there? One idea could be, well, since humans tend to have 80% of labelings as ducks and goose, my algorithm will be perfect when it makes the same rate of predictions, right? So making 80% of duck predictions and 20% of a goose on this image. The result of that is that in 20% of the time, the duck inputs will be wrongly identified, and in 80% of the time, the goose human example will be wrongly identified. So the N% of that is that this algorithm will get you 68% accuracy. Now, you could also have another idea, which is to say, I'm always going to say duck. And this works well in 80% of the time, right? So this is the best result. So your machine learning algorithm will naturally tend to do that, which means it will actually never label anything as goose. And you can, once you have trained your algorithm, you can look at which inputs are actually never in your end results, right? So you can identify that there are some labels that were in your training set that are never predicted by your algorithm. And that tells you that there is this kind of issue in the labeling. And so when you apply that to XBRL and you see that there are some tags that are never predicted, that tells you there is some large confusion in the way some tags can be applied. When we did that and applied that to prediction with large context, we thought that that was mostly applicable to tables and text blocks in notes. So I can give you an example, for instance, for US GAAP. And the one that is most common is on financial instruments. I think there are two tags in the US GAAP taxonomy that are disclosure of debt, table text block, and disclosure of debt instruments, text block. One of them, they have different definitions. One of them is for long-term instruments, and the other one is for debt instruments in general. And when we try to make predictions, it would always predict for us disclosure of debt instruments. So the one for long-term. That means that issuers actually use these two tags pretty much at random to tag any type of table that contains information about debt instruments. And when you go and look at the actual disclosures, you see that, yes, that is very much the case. Usually they will just use these tags conveniently to just, because they have two tables, so they will pick one for the first table and the other one for the second table. As users, that tells us that we don't actually need to have two tags that can be selected for a user that wants to see information about debt. So we merge these two tags in the taxonomy we give to our users, right, for element selection, because there is no actual definition. But that could also, of course, be used for taxonomy oversight or common practice oversight. We want to know, it's important that these two tags exist in the first place. So also maybe to make reminders to issuers that they have different definitions. There are other applications to inline XBRL as training sets than plain identification. So one of them is completion. Completion would be if you don't take the plain text as an input, but if you take the inline XBRL itself as an input. So that means you will use that, you will use an inline XBRL document as what you are trying to use, and that would be for completion. So for instance, we had example yesterday where we identified that there was issue with some reports where footnotes were not tagged. So in that case, you can train your algorithm to identify information by taking a whole XBRL document, then deleting a tag and trying to have it predict what the missing tag actually is, right? Then it can use not only the text, but also information about what other tags have been used to actually identify what the meaning of it is. One other way that can be used, for instance, is to get better prediction on newly published reports. So for instance, one thing that is very important for us users is timeliness, and there are many companies that disclose their financial statements before their financial report, and we need to give them information as soon as this is published. So usually we are very keen to actually try to look at the information that is plain text, identify what is the meaning of this. But it would give us disappointing results if we just took the new reports and didn't use the information that the company has already tagged financial statement the previous year. So we have a lot of information about how it usually makes its report. So our training set will be couples of reports, ones from year n-1 and ones from year -n. And our algorithm will be trained to recognize how companies usually tag successive reports. It will learn by itself that when companies use similar labels, it usually is the same elements, but it will also learn to identify cases where it is not so. It will learn to identify which elements are restatements and which are actually changes in definition, without us having to tell it, try to look for the word restatement or such, right? So that's one way we can also use that. Then I would like to talk to you about actual artificial intelligence, or what I consider it to be so, right? Right now, we've talked a lot about very classical machine learning, but there are some issues that cannot be solved with just training. And one of them is language. So we have many reports in English, but fewer in French and even fewer in Lithuanian. And 11 reports per year is not enough to learn about reports if you just try to train them on inline XBRL data. So that is solved by actually using unsupervised learning. And so I talked earlier to you about the task of trying to make a copy of something. So that can seem dumb at first, right? You're trying to make a program that makes a copies of a report. You don't need machine learning to do that, but I will tell you why it's actually useful. So the trick is in how you do it. So imagine you take pairs of translated text from English to Lithuanian, or pairs of equivalent text that is supposed to have the same meaning, and you choose to delete words from it whenever you use that. So you will delete some words from the English document and some words from the Lithuanian document. And then you try to reduce the size of the document into the most essential meaning. And your end task is to get documents as close from the English document and the Lithuanian document as they were in the beginning. Basically, your algorithm, to do that in the best way possible, is going to have to draw information from the other report. So if you deleted a word from the English document, it's going to have to identify which word or which part of the Lithuanian document did correspond to that and learn how to reproduce that. The end result of it is that the smaller documents, the ones that are compressed, are going to have the same structure, so that the document can know if I need a verb, I'm going to have to look in that position. So what you do once you have done that is you will be able to cut part of it and just take the part that takes your English document and makes a very compressed document from it. And that will be the source of your training. So you will train your algorithm to just learn about how to convert one of these documents into a prediction of a tag. And what is convenient about that is you also have, from the previous training, a way to transform Lithuanian documents into these smaller documents. So the training you could do on the 40K English documents can also be applied to that Lithuanian document. Basically, you were able to actually train to recognize Lithuanian documents on 40K English documents without having to need to actually make actual translations, right? Nowhere in there did we actually try to translate the Lithuanian report. Generally speaking, all tasks and all improvements we've seen in the latest years are in this kind of patterns. We train something to be very efficient at recognizing general patterns in documents. That's what you call pre-training. It can be done very efficiently because it's unsupervised. So we can just train on many documents, right? We can train on any kind of English and Lithuanian couple of documents without having to do some human labeling. Then we fine tune it. So we will try to get it to work on pairs of Lithuanian and English financial documents or documents linked to the taxonomy that's underlined. So we will use, for instance, the documentation of the elements that's given by the taxonomy. And then we have the final task, which is supervised training. So we finally use this transformation of general text into small patterns and use it to really predict what we want, which is, for instance, the meaning of the tag. And that's basically all of AI right now. The convenient thing about that is the gray part can be pre-trained or trained by other people, right? So us as Corporatings, we don't have the resource to train general language models. So we can use what Google or other make public through that, right? So that's what we call large language models. In themselves, they are not able to predict everything, but they contain very good understanding of what language is and how it works. But generally speaking, what I want to say is mostly you cannot afford not to make the last part. So no matter how much time you spend training a model to understand language, it will never know by itself what financial analysis is, what accounting is, right? So at some point, you need to tell it what it actually is. Imagine you take someone that is very clever and you just feed them the accounting standard. That's not enough to actually know how to make a report and how to understand a report. You need to have seen actual example and people explain to you actually what people meant when they wrote it, right? So that's the main message I wanted to give you, which is with all the work that we do on the gray part, the little blue part needs to be done. And we need these labeled documents, right? So that needs to be either inline XBRL, where accountants have identified what the document means, or it can be work like ChatGPT, where financial analysts will try to interpret which of two predictions are the best. But of course, it's better, in my view, if accountants are the one to say what is the truth of their document. So I wanted to make double thanks to you. So first for listening to me, and also but for creating this dataset, right? Even though that was never the intention of the community, we are able to use that to gain a lot of understanding about really how financial reporting works. So thank you.
Thank you very much. I think we've probably got time for a couple of questions to Marc, but great to be able to say that at the end. So perhaps the answer to our question is AI friend. Structured data. Any questions in the audience? Well, we really have got an audience now. Look, it's standing room only. Yes, Mike's coming to you.
Yeah, thank you. Thank you for the presentation. It's we learn a lot from it. Regarding that supervised part, where we looked at the very first presentation of this event, we saw that audited data was actually the best thing to use for AI. But do you think there's work to be done with auditors to harmonize their opinions about what actually is right and wrong? Because in my opinion, sometimes that is really unclear.
Oh, sorry. Yes, we can actually use that also to try to predict the conclusions from the auditor. Right now, on most of the reports, the conclusion is that everything is fine. So you cannot predict a lot of it. But if you wanted to train that, we need to, for instance, have the ability to get reports before they audited and then after they audited. So that's not public information. But theoretically speaking, if auditors kept that information, they could perform that kind of analysis to see really what kind of issues did we actually fix in report. I know that sometimes it's hard to oversee the actual work that was done within audit firms, so that could be interesting.